I'm planning on talking a little bit about LLMs and a little bit about how to fine-tune them and when you want to do it and when you don't want to do it. Normally, you don't want to do it. Small teaser. Exactly. So we'll check a little bit at the history on what happened there. What's the LLM conquest, basically? What would I call the modern AI dilemma, more or less? Small cases to just visualize it a bit for you. A decision framework that I personally think of when I'm trying to decide, okay, should I invest time to fine-tune something or not? And a little bit on fine-tuning itself. Right. And as I said, I'm Laurens. I'm a data and AI consultant here. I specialize by now, I would say, in maybe GenAI, but also have a background in machine learning engineering, data engineering. As a consultant, you keep on doing a lot of things. And I really like building data and AI products, teams, and organizations. So this is what puts me here today. Exactly. Small show of hands. Who of you would consider themselves a GenAI practitioner, just to get a rough feel? Okay, like kind of everyone. Nice. Cool. Glad. Then let's dive into it. So the LLM conquest, how did it all start, right? I think most of you, if you consider yourself GenAI practitioners, know this paper, 2017, attention is all you need. Transformer architecture, that's when it kind of picked up, started off. And then in 2018, we had BERT, one of the first original LLM architectures, right? So this is where you still started, okay, what can this actually do? How good is it really? And a little bit later, you have GPT-2, 1.5 billion parameters, if I'm not too wrong here, and around context length of 1,024 tokens. So for anyone who doesn't know that, it's basically how much of an input text corpus can the model handle, right? So 1,000, not too much. Next up, 1 year later, we have GPT-3, quite a bigger, quite a larger model, and already an increase in context, right? So by now, you start thinking, maybe I can, instead of just trying to bake the information into the model by like fine-tuning or training it, I can just give it to the context, right? And that trend kept on increasing. In 2022, we had ChatGPT launch. 2023, suddenly there's GPT-4, and this was quite good, right? It's 1.7 trillion parameters approximated. I'm not sure about the official number here. And you have 32,000 tokens context windows. So that's basically where you can start adding just entire documents, right? And then you just query that based on the context. You don't really need to give it actually to the weights themselves to train the model. And in 2024, I think we can refer to token explosion. Claude 3.5 comes in, Gemini 1.5, who claimed back then that they can handle 1 million tokens. Now this is debatable because it wasn't really performant. Well, you can add more and more documents to the model itself, right? It keeps on understanding the conversation history, for instance, and so forth. And in 2025, by now, we have established multimodal models. You can give it pictures, voice, text, and it works quite well. And you can give to it very large context as well. So these are off-the-shelf models that just work straight off the box. Normally, if you consider APIs by, for instance, Anthropic or OpenAI. So this as a little bit of background. And this brings us to the modern AI dilemma, at least what we observe a lot in our industry, which is basically the promise of Gen AI, right? At least this is how I see it. So GPT-5 and Claude can handle anything, right? You give it a task and they solve it for you. If they can't, you just need to engineer better prompts, like give it better context, right? Because then the model should be able to do it. And if the prompt is not sufficient, you just add more and more context, right? Because that should eliminate fine-tuning. And if this is still not enough, then hopefully the next model in a couple of months, couple of weeks, half a year, should be good enough to address your issue. So this is basically a debate that I observed quite a bit when talking to data scientists, when talking to practitioners, also to stakeholders in business, let's say, because it's always a question on when do you invest the time to actually build up training data and build your own model. And in 2025, where we are right now, everyone's talking about AI agents who build and do everything by themselves. Let's look a little bit at the reality. First off, we have specialized domains, right? So the models we have normally, like through third-party APIs or open-weight models in Hugging Face, they are rarely specialized to your specific company, to your specific industry needs. Depending on where you want to use the model, you have implicit institutional knowledge. So you have basically a process that used to work the way it used to work. You have maybe a person, a couple of people, colleagues, employees who have been doing this for 3, 4, 5, 10 years and know it, but it's not encoded anywhere, right? You want to have consistency at scale. So if you build it out, some models are non-deterministic. Sometimes they are creating something that you don't really want. So there's also a challenge. And you always have cost versus latency. So if you use the latest chain of thought model, reasoning model, it takes longer to give you the answer you need than maybe a very small one or a model that's not a reasoning model. Similarly, if you want to host it, maybe on-prem, maybe in the cloud, but in your private cluster, we're talking GPU costs, right? And if you want to host a 70B model on an H100 or something like that, it's getting easily quite expensive. Smaller models are much cheaper here. And this also ties in with the last one, which is privacy and compliance, right? Especially in healthcare, medtech, probably any regulated industry, you have this topic. Now, a little bit of example cases that we observe a lot in industry, right? Be it in media, in finance, in medtech even. Any kind of company has invoices, has artifacts that come maybe from a third party, from an employee, from a partner company. If it's already automated, then it's fine. But oftentimes you have someone manually checking the invoice. Is this what has been agreed upon when you signed the contract? Are they billing for something else? Where do I add this invoice? To which team does it go? Which department should handle it? And so on. So there's oftentimes implicit institutional knowledge that we find here. And these are oftentimes registered manually. And this is where you have document AI. So you have basically LLMs that can extract information here and parse it to whatever you need. But if you think about employees manually doing that, it's getting quite expensive, right? And if you think about just throwing the invoice to, let's say, Claude or something else, maybe sometimes it works. Maybe in more domain-specific contexts, it's more difficult. Consider, I don't know, construction industry, where you have sometimes invoices that are not that digitized, right? And when then your accountants, employees, any kind of office worker wants to understand this invoice, they have institutional knowledge. And then they map it to wherever this invoice needs to go. And this is not in an LLM. And this is also oftentimes not easily added to context. So this is where fine-tuning gets interesting. Different case, just for the sake of it, let's consider you have product descriptions, online web shop or something, and people upload their products that they want to sell, and they just write long texts. Maybe you just want to have a small fine-tuned model that can generate easily, quickly, good product descriptions. Also something where you want to adjust maybe the tone of voice of the model, right, to give it to your specific industry a better way of expressing itself and so on. This is also where fine-tuning can be interesting. Before we dive into this, let's consider the conceptual costs here, right? So let's say you have a very old company, or maybe a more traditional company, put it like that, and the process is manual, then you have zero setup costs, right? Because you don't change anything, but you have high ongoing costs because it's manual cost. If you use an off-the-shelf model, you have a low setup, you just call an API most likely. Generally, the performance is quite good, but you have high usage costs normally. And if you want to fine-tune your LLM, what you need to think about is you have latency and hardware limits, right? So it can get easily quite pricey if you want to fully fine-tune something. You need compute budget and so on. You need also domain adaptation. So that means training data, understanding what you want to fine-tune it on. And you have longer lead times and costs. So it takes a while to get the model to where you want it to get. But once you have it there, then the model does what it should do for your specific domain. And about the latency. So during training, you have some time that you spend quite a bit, right, waiting for it. If you have a smaller model afterwards that's fine-tuned, it's much faster because you can deploy it on a smaller GPU. And normally, well, speaking like that, smaller models can be considered faster. Exactly. What else do you need to consider? Again, performance, what do you want to achieve? Are you okay with a couple of seconds, or do you want like less than a second or even less so? Do you need domain knowledge? Any data privacy concerns? This is oftentimes the case in industry. What's the time to deployment, the time to market? Like how long do you need to wait before you can release the product? How much volume, right? Maybe if you just have 100 requests a day, that's fine. But if you have 100,000 requests a day, then third-party APIs get expensive. And again, as we talked about, available resources, right? Do you have people who can actually do that? And do you have the compute necessary? Right. Short disclaimer, fine-tuning is often not the first option for most GenAI use cases. So please start simple. If you consider doing this in your company, don't go and say, I want to fine-tune something. Consider first the options that you have available. So one of them is the baseline capability check, right? Can the existing models already do what you need to do? Just use an API, do a little bit of prompt engineering, featured learning, whatnot. Most of the time, it gets you quite far. Second one is, as we talked about, the deployment and privacy check, which basically means, is the data confidential? Are you working in a regulated environment? Is it proprietary? Maybe you want to use an on-prem setup. Then if you want to host large models, then you need very big compute. Otherwise, maybe VPC in cloud, encrypted data, and so on. So this is oftentimes something that we face actually in projects, right? And this is where you then need to consider how you deal with it. And now let's look a little bit at the problem types that at least I've seen quite a bit. Probably there are more out there, but you can basically classify it in, is this a problem that relates to knowledge retrieval? So do you already have knowledge somewhere structured, for instance, in documents, in pictures, whatnot, in slides? You can use RAG, so retrieval augmented generation. By now, I think everyone here understands this, so I'm not going to elaborate further on it. Otherwise, please screen. Do you require external tools or functions? So do you need access to the internet, for instance, the database, to another application to do some business logic? Then you can consider agentic approach, using tools to call and so on. This is where the hype right now is a bit, right? Because you can automate a lot. But if even then the model does not have the information it needs to solve your problem, and if you have proprietary private data, and if you have institutional knowledge in this process that you want to automate, then consider fine-tuning. This is kind of a rough guideline that at least I try to follow. And so far, it's proven me quite well. Exactly. So fine-tuning commitment checklist. You want to validate your problem. So clearly define success criteria, metrics, what's the baseline performance that you get with off-the-shelf models. You want to get stakeholder buy-in, of course, because you need longer than the GenAI application that's promised in like advertisement, right? It's not just 1 day, 1 week, and you're there. And it might cost a bit more. Data validation, you have high-quality training data available, right? Depending on your use case, that can be quite tricky. Also, does it represent, of course, with any data science problem, does it represent the official population of what you try to train on? Do you have proper labeling qualities? So this should be verified by domain experts, especially in this type of context. In this type of a context, right? Maybe someone might say, if they see a text, this text belongs to persona A, and if a different person, a colleague, sees this text, they might decide persona B. So you kind of need to have this consistency check here. And again, of course, consider edge cases, failure modes, where maybe the domain knowledge that you think you have is not sufficient. Finally, resource validation. Technical expertise is available, compute is accessible, timeline is realistic. And any red flags. For instance, do you have a use case creep? What does it mean? That means that initially you think, yeah, the model right now, we have all the cases that the model needs to handle. And then half a year later, you realize, okay, that wasn't enough. Because then you can train from scratch, essentially. If you have corrupted data in any data science project, that's a problem. But if you want to train a larger model, that's even more so of a problem. And if you expect 100% accuracy from day one, again, these models are normally not very deterministic, right? So you cannot make the claim that you always have perfect responses. Exactly. This as a little bit of a disclaimer before diving into. And before we do the techniques, let's maybe first understand what the LLM really does. Most of you probably understand this already. It outputs a probability distribution over tokens. So it kind of determines or predicts what's the next best token over distribution. And that is basically what happens during the inference, right? And when you do fine-tuning, you want to improve this performance of this existing model for the specific use case. So maybe change slightly which next best token would be predicted, right? And normally in instruction fine-tuning, this is what we'll focus on here. You have training data, so you have an instruction query, and you have a response pair. So you have kind of the query and the pair as the query and the response as pairs. And with these prompt completion pairs, you can train your model. And then basically, as usually, you have some sort of loss function. You see what was a correct response, what was an incorrect response. And then you just, kind of do, again, the kind of model updates and improve the model by doing so. So that's in a high-level nutshell, right? Exactly. And as I wrote here, the model then learns by comparing the predicted next token distribution to the target distribution, right? So how far off are we, and how strong do we need to correct it? Exactly. That is as a disclaimer. Now let's dive into the instruction fine-tuning techniques. So there's commonly full fine-tuning, which is basically you just throw the entire model at the training data corpus that you have, and you update all the weights. What's the challenge here? A challenge is, first of all, that if you have a large model, you need a lot of GPU compute, and it takes also a very large training data corpus to actually address your problem. If you go on Hugging Face, for instance, and you looked at instruction fine-tuned models, like most open weight models here are instruct fine-tuned models. And just as an example, you have your prompt completion pair here. So for example, I love this product, and then the completion should be this is a positive response, right? This is how you can train it. If you do full fine-tuning, the common problem here is catastrophic forgetting. So that means that normally models are trained, or LLMs are trained on different tasks and different categories of tasks. If you change all weights, you might just destroy the previous capability to respond to these tasks, right? Exactly, and just again to say, it is very expensive and most unrealistic for most use cases as well. Just because, yeah, you don't just have the weights, you have a lot of other stuff, and it gets expensive. Now, what else is there? Is parameter efficient fine-tuning, PEF for short. And what you do here is you freeze most or all model weights, basically, and then you train a small, basically tasks that pick it up to data and parameters. Different versions of parameter tuning. I'm going to focus on LoRa and QLoRA in this case. And the good part is manageable memory. You have a much smaller subset of parameters that you want to fine-tune, so you don't need as much compute, you don't need as much training data, and don't need as much time. During inference, parameters and original model weights are then combined, so you also don't have catastrophic forgetting because you keep the original model weights alive, basically. And exactly, if you want, you can either do LoRa or QLoRA. At least that's what is currently supported by VLLM. So if you want to deploy your own model and do inference, there are also, of course, other techniques out there, but then you got to check if your inference runtime and like serving time can actually deploy this model and work it. Let's look at LoRa in a nutshell here. So any one of us with more or less high-end GPUs can apply it, which is quite useful. And you don't need a kind of crazy data center infrastructure compared to what you previously needed if you were doing full fine-tuning. And you basically freeze your original model weights. Per weight, you inject 2 rank decomposition matrices. So this is kind of trickier. To train in place of the original model weight matrix. And those rank decomposition matrices, as you can see here, are of a much smaller rank. And by only focusing on these, you also need to only train a much smaller subset of parameters. So here, just as an example, right, in the first case, if you have these dimensions 64 by 512, you have like 32,000 parameters. And if you do this rank matrix decomposition, you come to around 4K parameters, which is quite a bit smaller, so 86% reduction. Exactly. And what is the good part about this? It's basically enabling you to change the behavior of the model, maybe change the output of the model, like give it a different structure, or even bake in some of that domain knowledge that you want the model to have. And it comes at the cost of a price of full fine-tuning. So that can be quite, quite worth considering if you have the use cases. So if you have the correct data for training it, and if you actually want to do it. And once you have your LoRa adapters, for instance, with in NVIDIA, I think it's Nano, which you can deploy it with. In open source software, you would want to use VLLM, right? And you can just deploy your base model and your LoRa adapters on top of it. And if you have different use cases and a lot of training data and you have different LoRa adapters, you can even swap it. You could even swap it at runtime. So you deploy the model on the GPU. For use case A, you load in the LoRa adapters for use case A. For use case B, load in the LoRa adapters for use case B, at least in theory. Exactly. You could also do QLoRA. So this is, again, a quantized version of LoRa. I'm not going to go into detail here too much. I think as a ballpark figure, QLoRA, I believe, is more efficient during training. LoRa is a little bit more efficient during inference. But again, that's just something that some people tested. You can happily also test and report back what your findings are on this. Depends a little bit on the use case on the model. In practice, you don't need to go through all this code here, right? Just to showcase, if you, for instance, use Hugging Face, it's quite easily doable, right? Like you have your transformers library, you add some stuff from the PEFT library, you load your base model, your tokenizers, you set your LoRa config. So what's the rank you want to have? Some of the hyperparameters that normally I think you can just safely take from the LoRa or QLoRA paper. They report quite a few of these. You train your parameter efficient model, so your PEFT model with your training data. And then you have your model base and your PEFT model where you just load the adapters from the path. So wherever you basically saved your adapters on disk, you load them from there. Now this is if you want to actually do it yourself. Of course, if you look at the hyperscalers, so GCP for sure, I know, AWS as well, I expect Azure by now to have the same functionality. They can they offer tuning at a button, right? So if you go to Vertex AI, normally you can give it your training data and just say tune it for me. You don't need to write all of that, I would suppose, but it's good to know how it works. Exactly. So looking back at one of the examples, now this is not an example of an actual client of ours because obviously those are confidential. But just if you look at, let's say, the model, some LLM, and you want to have a base generation. So this is the product description we earlier talked about. And now if you say, I want to have more punchy, to the point, more concise product descriptions, this would be the output here. Courtesy by a blog I follow, Phil Schmidt, very good blog. Exactly. This is basically fine-tuning in a nutshell. And this is how you can adopt it also in industry, in your company, if you're interested. As a summary, don't start with fine-tuning. Follow the decision framework, if you like, so the one we checked out earlier. Consider context enrichment, consider RAG, consider agentics, an agentic approach. This gets you fast, normally. When you consider fine-tuning, again, validate your data set. You don't want to train a model and then find out that it doesn't work properly. Validate that you really need this institutional implicit knowledge, right? So something that you don't have as structured data you can add to context, but actually something implicit. And also do not expect a silver bullet, of course. It only gets you so far. During fine-tuning, something I observed. So Hugging Face libraries can change a bit. The models can change. So if you use, for instance, vision models, then depending on the architecture, it's a bit weird. Sometimes you can fine-tune directly with those libraries. Sometimes they have different components and you need to find a different way. Exactly. So for QLoRA, you have higher training compute efficiency, and for LoRa, normally you have better inference speed. And also, again, as every one of us knows, at least who has done something similar like this, don't reinvent the wheel. There are a lot of notebooks out there. There's a lot on Hugging Face, on GitHub, where you can just pick up from. Exactly, that's as an outline to when you want and when you don't want to actually fine-tune your language model.